I wish I could come last week as well, but I was traveling. I mean, it has been really, really a nice event. I am very glad that Fred invited me also to take part in this event. I mean, I was actually there when he was having his initial ideas of gathering people of coding theory and cryptography together. We were having lunch at the canteen. We are also office mates with him. So, I mean, I was there when his initial ideas were about, okay, maybe we should do something about more cryptography and applications, and also codes for cryptography, etc. So I hope, I mean, everything you dreamt of is actually happening. So it has been really a nice event, and I am also very glad to see, I mean, quite a number of students, also quite a number of female students. I mean, that always makes me very happy. I mean, for the ones who don't know about me so far, my nationality is Turkish. I am from Turkey. I am born and grown up in Istanbul. So, but currently I am working in Singapore, but I'm from Turkey. I did my PhD and everything there. Well, that implies I have had uniforms like Fred did for 11 years. This is how it happens, right? I mean, also, I mean, from my times, I can simply say, I mean, for a girl, especially for a girl, it is not highly expected to be here, right? I mean, that's why I hope all the lectures here were a bit inspiring for you and also encouraging for all of you to become part of the academy. So, I will stop with the introductory stuff, and let me go over the history of so-called LCD codes. Oops, okay. Which one is the forward one? This one, I guess, yes. So, basic definition. A linear code is called LCD, which means linear complementary dual, if it intersects with its dual trivial way, in a trivial way, only the zero code word. So, they are initially invented by Massey in '92, but the motivation was really channel coding. He invented LCD codes, or proposed LCD codes, as a solution to a two-user binary adder channel. That means you have two users who wants to send some data through some discrete channel, okay? What you send is x plus y, where x is coming from the first user, y is coming from the second user. The problem is to decode it, to make it decodable. If the dimension of the two codes are higher than the code length, then it is not decodable. That is proved by Patterson and Costello, I guess. So Massey proposed LCD codes as a solution for binary adder channel for two users, so that one vector comes from C and one vector comes from C dual, and that is decodable. So that was his motivation. And with Young, they studied LCD cyclic codes by giving the characterization, I mean, a cyclic code is LCD if and only if it is reversible. That is equivalent to say that the generating polynomial of the cyclic code is self-reciprocal, okay? And that stops. Years after, Nicolas Sandrier studied the asymptotic properties of the LCD codes, but just for mathematical purposes actually. He showed that they satisfy a modified Gilbert-Marshall bound, plus he said the LCD codes have a higher density once you raise the size of the base field that the code is defined. I will come back to that. And LCD codes are then rediscovered in 2014 in the framework of orthogonal direct sum masking, which is a countermeasure for side channel attacks and the fault injection attacks. And actually, I am very grateful that Jacob provided me a perfect background. He actually explained to you how they are actually performed in the engineering side. Okay? Today, I am going to talk about, I mean, how they are observed in the discrete sense, in the, I mean, what happens to the original digital data that we are sending to the channel, and how we can prevent such attacks being successful. But really, I mean, I really have very little idea about the engineering part of it, so I am really grateful to Jacob to that he provided really nice background about this. Because from my point of view, side channel attack is, I mean, when you are in a room, right? I am just a mathematician. I mean, I am just trying to simplify stuff to explain you. We are in a room, we are chatting, I mean, or conversating or arguing about something between two people, and outside the room, either behind the door or behind the wall, there is someone having a glass and trying to listen to you. That is side channel attack, okay? The device that is used is the glass, okay? There is a leakage of information, okay? The information leaked can be anything. It can be sound, it can be, I mean, as Jacob said, it can be image, it can be electromagnetic, anything. From mathematician point of view, the leakage is characterized by a map from digital, I mean, FQTDN, to reals, okay? Leakage is usually analog, so to say, okay? That's how we characterize it. So, what is orthogonal direct sum masking then? Let me start by the famous characterization, sorry. So, the LCD codes are characterized by Massey by this famous characterization, GG transpose, okay? When you have a generating matrix for the linear code, then GG transpose must be immutable. By the way, I inserted some proofs in the slides just because they are going to be put online, but that doesn't mean that I will lose a lot of time with the proofs. I just put them so that, I mean, if anyone is interested and wants to go back to read it, some proofs, some easy proofs are there. So, this is the proof of it. And the idea is simple. For one way, one goes from the contradiction method, of course. Let's say C is LCD and GG transpose is not invertible. Then, this homogeneous system has a non-zero solution, let's say U. So, U times G must be a non-zero code word of C, and let's choose another code word V times G, and then take the Euclidean inner product. And it is 0. That means UG is in the dual, which is a contradiction because the intersection with the dual was trivial. So that is the method. For the converse, it is easier. Let's say GG transpose is invertible and choose someone from the intersection. Then once you take the product with G transpose, you obtain 0. And that makes U equal to 0 because we assume GG transpose is invertible. So the homogeneous system has unique solution, U is equal to 0. So, very easy linear algebraic proof. And then, I mean, he really proposed that for the binary 2 user adder channel. And years after, let me go over the orthogonal direct sum masking. So, I will go over binary, okay? I mean, that applies usually for general channels over FQ as well, but binary is easier to understand. And also, it motivates the initial intent to protect the data. So let's say you have an information to send of length k over some binary channel, okay? Let's say it is x. So, you encode this data by using any linear code with generating matrix G. The encoded code word is x times G, okay? But instead of sending x times G directly to the channel, you create a mask, okay? A mask Y, which is encoded by another matrix H, which has a complementary dimension with respect to G, okay? If G has dimension K, then H has dimension n minus K, okay? So, Y times H is called the encoded mask. So, instead of sending x times G directly, you are sending this Z. I mean, XH plus YH. It corresponds to like saying, I mean, if you suspect anyone is listening what you are talking with your friend in one room, then you can switch to, let's say, half English, half Indonesian, you know. I mean, saying some words in Indonesian, saying some words in English, that corresponds to this type of masking, for instance, okay? I mean, just any masking you can think of. So you send a mask data. But of course, I mean, the purpose is to protect X and also to retrieve X and Y in the end. I mean, you have to do that in a unique way, okay? So, C and D can be the codes having the generating matrices G and H respectively. They can be considered as two separate codes. And of course, LCD codes can provide a uniquely determined decoding for this problem, okay? Once you set the intersection of these two codes to be trivial, then this becomes uniquely retrievable for X. So, the LCD case, you have the D equals to C dual, okay? So that C, direct sum C dual becomes the entire space. And this is how you obtain the vector X from Z. Once you receive Z, in a noiseless way, by the way, I mean, this is not our concern right now. Our concern is to protect X. That I should emphasize. So, once you receive Z, by multiplying with this huge product of matrices, you can retrieve X, okay? You can do the calculations by hand. I mean, it is really easy. And similarly, you can do it for Y, okay? So, this is how orthogonal direct sum masking works. So, I said some words about the side channel attacks, but of course they are well presented by Jacob himself. I will just mention you, I mean, those codes, those type of codes are good for three things, actually, three types of fault attacks, so to say. Side channel attacks, fault injection attacks, and also hardware Trojan horses, all of them. I mean, Jacob mentioned yesterday in his talk, if you recall, I mean, the classification of fault attacks. So those happen to be a countermeasure for all of them. So since side channel attacks are hard to be explained in the discrete level, I will try to give you the example of fault injection attacks and how we observe the fault in the discrete sense, okay? Just as an example, let me start. So, how orthogonal direct sum masking resists the fault injection attack. So let's say we have an intruder who injects an error, who manages to inject an error epsilon, let's say, into Z. So what happens in that case? I mean, of course, the main purpose is to reveal X. So we have an LCD code here. The intersection is trivial, so their direct sum gives the entire space. That means there are vectors E and F that are uniquely determined by this direct sum, so that E is in C and F is in C dual. Okay? Those are uniquely determined because of the direct sum. And the corrupted word is Z plus epsilon. So what happens? I mean, if we analyze this code word, I mean, can we detect it or not? That is the main purpose once Z plus epsilon is received. Here is what happens. We check Y during the process, okay, or mask, if it is successful or not, and it is successful as long as F is not 0. Okay? Once F is 0, then the fault attack is successful. Okay? So, what you should do in that sense is that to keep the distance between this E and F as big as you can. Okay? The Hamming distance. That means you need LCD codes with high distance, high security parameter. DC is your security parameter, so if this is high, then injecting some E times G into Z costs a lot. I mean, not only money, but also time, also a lot of effort, okay? High distance signals are hard to be attacked, okay? But this is one countermeasure. I mean, it is successful as long as it cannot reach the distance of the LCD code that you inject. So, a more general setup is LCP, linear complementary pair of codes. I mean, this is when C and D directly sum up to the entire space in the general setup FQTD. And I mean, the definitions hold, of course, I mean, for any finite field, and LCD becomes a special case of it. I mean, both classes are good for orthogonal direct sum masking, and this is the purpose. I mean, to resist side channel, fault injection, and hardware Trojan horses, and any such type of fault attacks. Okay, that is the purpose. So, I just want to mention very briefly how things work for the hardware Trojan horses by only a few sentences. Okay. In case of LCPs, I mean, this is a paper of Guillet et al., Guillet, Jean-Luc Danger, and three more authors, I guess. So, in the case of LCP, the security parameter is no longer DC, but this minimum. Okay? In the language of hardware Trojan horses, this is the trigger parameter, and this is the payload parameter. Okay? Once a Trojan horse is inserted into the system, you cannot remove it. The best you can do is to avoid the leakage of your data. Okay? So what does a Trojan horse do? First of all, once it is inserted, it starts reading, probing the leaked data. Okay? So here is your trigger parameter. The trigger parameter characterizes that reading. So if the Trojan horse can read some bits which is strictly less than this parameter, then no data is revealed about X, the initial X that you the data that you have masked already. Okay? Once the reading, the probing of the Trojan horse is strictly less than this parameter, then you are safe in that sense. And also a Trojan horse does change the data. After reading, it does start changing the data. Okay, modification. So this is your payload parameter. So as long as it changes at most that much bits, then it is detected by your hardware. Okay? So if the Trojan horse changes at most DC -1 bits, then still you are safe with your X. So you have to take the minimum of those two parameters to make sure that, I mean, you can get rid of that Trojan horse before any catastrophic change happens. So that is one of the uses as well, I mean, in that language. So I won't go any further in the history of that. I will just tell, I mean, for the LCD case, we don't have two parameters, I mean, trigger and payload, we just have DC. That makes things sort of easier, of course. I mean, instead of dealing with two parameters and trying to optimize them, you just have to optimize one thing. So, in the end, we want LCD and LCP codes of huge sizes. I have one more thing to say before going any forward. So, you see, this is about the usual Hamming distance of the codes. Last year in the SIMPA school, we had one important lecturer, Erdal Arkan. Have you heard of him? Anybody heard of him? Yeah, you of course heard of him. He is a professor in Buket University in Ankara, and he is the Shannon Prize winner of this year, because he introduced the polar codes. So he had one very particularly important note during his lectures by saying, okay, in terms of channel communication, okay, where you encode the data, I mean, in terms of some linear code and send it, and your error detection is DC -1, your error correction is DC minus 1 over 2. So, I mean, all those stories are over. The study of minimum distance, because this is, I mean, since maybe 60 years, everybody is searching for good codes in terms of minimum distance, and that research is over. Because everything is about now channel polarizing, okay? The polarizing the channel. Right now, all these, all the algebraic codes have become part of algebra, applied algebra. Yeah, I am telling you, I mean, that guy buried all that research from the application down to the algebra level again, unless some applications like this. So the minimum distance of the classical codes are still important in that sense, information security. And also quantum stabilizers, like Fred mentioned to you yesterday. They still characterize certain error correction capacities of quantum stabilizer codes. Okay, except those applications, well, the minimum distance of the linear codes are no longer that much important in the channel communication. I am telling you in case you want to apply for some projects concerning this. If anyone knows, I mean, about this sad but true fact, then your project can return. So your motivation must be solid. I mean, right now, actually it was LDPC codes first. I mean, the last, how to say, high performance codes with high minimum distances, but which are mostly constructed in a randomized way. Okay? But after that, the minimum distance is no longer the concern, I am telling you. I mean, it is the channel polarizing. Right now, they are interesting either from mathematical sense. We still try to publish papers, of course. I mean, that some certain class of codes with certain types of constructions achieve some good distances. But those are interesting now from theoretical point of view, not from applications point of view. So that is one thing to be emphasized. I mean, please be careful once you are applying for projects and what you are really emphasizing, okay? So, they still matter for LCD codes because they are good for information security in terms of side channel attacks, fault injection attacks, etc. You can avoid such attacks up to the distance of the codes that you use for masking, okay? That is the motivation. So, today I am going to talk about certain papers. One is this, about LCP codes, the general LCP codes. First I will mention some stuff from there, and also LCPs of abelian, or the AKA and the cyclic codes, okay? But there are, of course, further constructions of linear complementary pairs. I mean, before going to LCDs, I will mention just a few things about the LCPs. Further works are done the LCP codes from algebraic geometric codes. I mean, that paper is mostly about that. And also a super recent one from group codes. Group codes generalize abelian codes in the sense that the group that you are working in the group algebra is no longer commutative. I mean, it doesn't have to be commutative, it can be any group, okay? So that work actually generalizes the second work above. So let me start with some basic notions here. The linear complementary pair of cyclics. So the theorem says, of course, I mean, it is given in technical terms, but what I am trying to say is that, I mean, if you have two cyclic codes C and D, okay, in order to make them LCP, then you have to make sure that the product of their generator matrices give x to the n minus 1. That is one thing. But, I mean, it is not enough. It is enough in the separable case, in the semi-simple case, I mean, so to say. If n is relatively prime with the characteristic of the base field, then it is enough. If not, if you also consider the repeated root case, then you have to make sure that all the repeated roots are well separated as well, okay? So, any factor of x to the n minus 1, any factor of x to the n minus 1 should be packed with all its algebraic multiplicity in those two factors, okay? You cannot sacrifice even one single algebraic multiplicity of each factor. That is what the theorem says, okay? So, this generalizes the Yang-Massey characterization of LCD of cyclic codes, okay? They say it was about being self-reciprocal, which makes sense if you consider LCD codes where D is equal to C dual, okay? The dual is always characterized by the reciprocal of the polynomial that you take here. It would have been then U reciprocal in that case, okay? And then U reciprocal must have been equal to GX. So, one interesting result is that, I mean, once you are working with LCP of cyclic codes, you actually don't need LCD. This is what this result says. Because C and D dual are equivalent. Remember that, I mean, in the LCP case, the two parameters that we are interested in was the distance of the code C and the dual distance of D. So if they are equivalent, then those distances are equal. That's why it is interesting, okay? I mean, in the case of cyclic codes, you don't have to restrict yourself to the special case of LCD. You can directly work with LCP. They naturally give you an equivalent pair. I have put the proof here, which is super easy. I mean, you can read it if you have time or if you have interested. So, the equivalence is generated by this G0 inverse, 1 over G0 in the monomial sense, and the permutation is sending I to n minus 1 to minus I. So, this is the equivalence. And this result actually tells, I mean, finding the best cyclic LCP of cos CD, the best complementary pair, is equivalent to finding best cyclic code that you can find in that length and dimension. Okay? So, you just have to look for the best possible cyclic code that you can get of that length in order to have a high security parameter. Okay? So, the same result holds for 2D cyclic codes. 2D cyclic codes are ideals in this quotient ring, which can be viewed as abelian, of course. I am coming to that very soon. So, but the result for this is rather complicated. I skipped that. I mean, if you are interested, you can read it from the paper, of course. It uses a lot of trace representation, of course, and then some results from algebraic geometry. I mean, explicitly some results from Artin-Schreier curves that is required to prove that result. And also, I mean, multivariate polynomial rings are not very easy because it is not PID. I mean, you lost the PID one step before. This is UFD. So it is a bit complicated, but the same result holds for 2D cyclic codes as well. The same doesn't hold for quasi-cyclic. I mean, they're closely related, of course. I mean, 2D cyclics are just a special case of quasi-cyclics, having two shift invariances. Quasi-cyclic codes have just one shift invariance, but in multiple bits, so to say. Okay? That means we have counterexamples for quasi-cyclic codes, I mean, linear complementary pairs, where C is not equivalent to D dual. Okay? And it is still open, by the way. I mean, how to find such pairs where C is actually equal to D dual in the quasi-cyclic sense. I mean, if anyone is interested, please go ahead. So, what happens in the most general setup, I mean, abelian codes, is that, I mean, of course, I mean, once you have an ND cyclic code, you can draw an equivalence to the group algebra notation like Griezmann mentioned to you 2 days ago. Let me go over even more briefly. Again, I mean, he provided some background for me. So, this quotient ring is isomorphic to this group algebra, where Cn is a cyclic group of order n, of course. And this bivariate quotient ring is isomorphic to this one, where you take the tensor between two cyclic groups, finite abelian cyclic groups of order n and m respectively. So, conversely, by using the fundamental theorem of finite abelian groups, which tells us that any finite abelian group decomposes into a product of cyclic groups, you can do the other way around, okay? And given any abelian code, you can represent it as an ND cyclic code. So there's a one-to-one correspondence. Once we have that, I mean, the nature question is that, I mean, I have that relation for cyclic codes, for 2D cyclic codes. Does the similar result hold for the abelian codes in the most general setup? I mean, it's a nature question, and it happens to be yes. For semi-simple codes, semi-simple means the code length is relatively prime to Q, the base field size. Okay? Now I will go over the method that we use to prove that. I mean, for the algebra emphasizers at least. So, as I said, the one-to-one correspondence is here. Once you have this n-myriad quotient ring, the group algebra notation, the corresponding group algebra notation is here. And as I said, each MI is relatively prime with the base field size. That is called the semi-simple case. The other one is repeated root case. I mean the opposite. Once you have a bigger greatest common divisor. So, what we consider is the zeros of the abelian or the ND cyclic codes. It is very similar to the case of cyclic codes. We consider the zeros with respect to the each variable. Okay, from x1 up to the xn, we have ideals in this quotient ring. The ideals living in here are called abelian, living in here are called ND cyclic, and we consider the zeros which are represented in that way. And of course there is a one-to-one correspondence between the zeros here living in that big set omega, which is the direct product of all the possible mth roots of unity, okay, which is finite. I mean, it is something like that, so we can count all the abelian codes in that sense, okay? There is a one-to-one correspondence, Seidenberg's lemma, which is completely geometric. So, but I just want you to believe that fact for now. So, the zeros of the abelian code C is the union of orbits here, okay? Which is closed under the Frobenius isomorphism, right? I mean, if you have a zero of the multivariate polynomial, the next one will be the Q powers of that. Let's say we have an element here as a zero of our code, so then alpha 1 to the QJ1, up to alpha n to the Q times Jn is also another zero. So that is what is meant. And therefore, you can construct orbits with respect to the cyclotomic coset, with respect to each variable, and voila, you have all the zeros of the abelian code. Using that, you can simply say, I mean, if I give a name U to the zeros of the abelian code, which is a subset, of course, the entire m's roots of unities, then the dimension of the code is, of course, characterized by this. Just like in the cyclic codes, remember that, I mean, the dimension of a cyclic code is just m minus the degree of the polynomial. Okay? So, what does fundamental theorem of algebra say? Here is the degree n, I mean, of the degree k of the generating polynomial, so I have k roots. So, the dimension of the code is n minus k in that case. And the similar result. Okay? So, once you have all these tools, LCP is characterized by the by this omega set and all the zeros. Here, the union should give omega, the entire mi throughs, I mean the big set of all the roots, and the intersection is empty. That is being LCP, and of course, you need that for the isomorphism. I mean, if you want to find the dual zeros of D, you have to take -1. I mean, if you have alpha 1 to the J1 and until there, so an element like this, here, you have to take -J1 up to -Jn for the dual zeros of D. So once you have all these tools, once you prove all these tools, the isomorphism is again analogous to the cyclic case. I told you, I mean, the monomial equivalence is run again by these elements, and this corresponds to the very same permutation that takes ith coordinate to n minus 1 minus I, right? I mean, it is the same coordinate-wise right now with respect to the each variable, okay? I mean, then the result is analogous. To generalize this result to the repeated root case, you need a result from Griezmann et al. He says he has proven that being LCD is independent of the repeated root part. In the group algebra setup, that means, I mean, you have an additional CLP group as a product. In the repeated root case, you have this. And you require that CLP group considered as another component to component here, okay? But he has shown, I mean, that paper shows that being LCD is independent of the PC group of the entire group G here. The entire group is this entire product. The only thing that you have to do is that to generalize it to LCP case. That's it. And it also happens to be working over the chain rings as well, not only over codes over finite fields, but also codes over finite chain rings. So all those results are, I think, a recent preprint about that. So let me continue by this work. So I have one co-author here, Ling Sok. So this is the first work, actually, that I got involved in that LCD-LCP business. Okay, I mean, Claude Carlet and Sylvain Guillet, those two are the rediscoverers of LCD codes. So they are both French, and they are, I mean, working in Paris. And guess who was a postdoc in Paris, I mean, right 1 year after that. So it is just coincidence, let's say. I mean, I went to Paris in 2015, I mean, where they were very ambitious about this LCD and LCP code stuff. So it really brought a fresh breeze, by the way, to the research of algebraic coding theory as well, right? I mean, many contributors published many papers about many constructions about such type of codes. I mean, in the mathematics research, we always need some fresh breeze in terms of topics. I mean, because the classical topics are so well studied, the remaining questions are so hard to deal with. It is usually harder to perform some research in the classical theoretical parts of algebra, even in coding theory. I mean, since 40s, 50s, I mean, many code classes are very well studied, and the remaining questions are hard. That's why we are all waiting for, I mean, such fresh new topics that are less studied, that you can, how to say, that you can contribute as a pioneer, right? I mean, we all are looking for such new areas of research, and that was one of them. I mean, maybe one of the most recent ones. So in the theory, that has been also a very important topic and very hot topic in terms of studying, but many coding theorists don't know about the fault injection attacks or the side channel attacks. They are not actually interested in that. They are mostly interested in constructing good LCDs or good LCPs from the constructions that they know the best. On my case, it is quasi-cyclic. I mean, most of my research is about quasi-cyclic codes and their generalizations. So naturally, I attack this case. But there are many other constructions like AG codes, different types of cyclic, quasi-cyclic, whatever, or from linear codes, or from lattices. I mean, you can find hundreds of contributions right now. But in this school, I really was wondering, I mean, if I can at least give you the notion of LCD codes, how they are good for the crypto applications. That's why I am really recommending you to read those foundational papers of Carlet, Guillet, and Guillet et al. About the side channel attacks and the hardware Trojan horses and how LCP and LCDs are good for it, okay? So, This work is mostly about binary LCD codes, linear codes, okay? That will start a bit lightly, of course, I mean, how you can use the basic knowledge of coding theory to construct the, the easiest possible LCD codes that you can create. So, let me start with the so-called fixed length and dimension. That means you are given n and k, as the length and dimension, what is the best you can do in terms of minimum distance, okay? So what we are considering, again, I recall they are binary. The first idea you can get is that, okay, if you have LCD NK, by adding a 0 column to the generator matrix, okay, extending it, you can obtain this one. The proof is just saying that. Add a 0 column, okay? The first idea that you can think of. You get an n+1 with the same dimension and same distance. So, what else? If n is odd, in the binary case, you have the repetition code, okay? And it's dual parity check code. The simplest possible, simplest things that you can think of. If n is even, then repetition code is self-orthogonal. It is contained in the parity check code. For that, you have to put your foot one step down. So it becomes n-1 and 1. Here, the proof, whatever I said in words. So for the second case, where the parity check code becomes self-orthogonal, then, without loss of generality, of course, you can set one coordinate to 0, so that you go back to the odd case, n-1 is odd, and you can use the previous result, okay? So, the easy ideas. And then, here we continue with the Kronecker product and the direct sum. You can use the Kronecker product of codes and also the direct sum of two codes. Once you start writing, okay, it looks a bit longer, but what you use is taking two codes and take their Kronecker product, of course. You can read them later. I'm leaving the proofs here. And also the direct sum satisfies these properties in terms of the code parameters. Okay? What else? In order to set some bounds, you have to know one fact about MDS conjecture, especially about the binary codes, that, parity check and its dual repetition code are the only MDS codes we have except the full space code. Okay? The full space code is naturally MDS in the sense that, the intersection with its dual 0 code is the 0 code. Technically we should count it as MDS as well, where its dual 0 code is not. That is that sounds a bit awkward. The 0 code itself cannot be LCD, technically, but the full space code can be counted as LCD. And that is the only case where C is LCD, but the dual is not. Otherwise, of course, there's a symmetrical relation. So, the proof is here. I recommend you to read. Why we cannot have binary MDS codes except those. Okay? I don't want to make you all sleep before the break, so that's why I won't read line by line. Instead, I will continue with the other constructions. Let's start with the smallest possible one, okay? This is what we checked over the magma, of course. Smallest possible, that makes sense, 3, 2. If you have length 3, dimension 2, the best you can get is 2. Why? Because you have the parity check code. And it is LCD. So, you can easily verify this over magma. 4, 2 is 2. Not 5, not 3, of course. If it could be 3, it would be MDS, okay? It cannot be. And what we know is that you had, there are several ways. You had 3, 2 equals to 2. Add 1, 0 column, as I said before, the first property that I told you, you get 4, 2, 2. Okay? That is super easy. And by coincidence, this command over magma gives you a binary LCD code. I mean, that is another thing. The code that is chosen up to the equivalence is LCD. I mean, if it was chosen another thing up to the equivalence again, maybe it wouldn't be LCD, but this one is LCD. But again, as I said, I mean, just add 1 0 column to 3 2, you obtain 4 2 2. Okay, what about 5 2? Up. It is 2, not 3, not 4. 4 cannot be. So here is the reason. Again, by that MDS property, as I told you, it cannot be 5 2 4. So our candidate is 5 2 3, the next one. But once we check all the 5 2 3 codes, I mean, their automorphism group is generated by those two codes. Huh? None of them are LCD. So we are left with this. But of course, since 4 2 was 2, by adding again a 0 column, you can easily obtain a 5 2 2, and apparently this is the best you can do. So, just using linear algebra and certain properties, you can really, I mean, that means once you have an entry over the table, okay? Over the same dimension, you can simply continue over the higher length, okay? That is the idea. And this is 6 2. Which can be done over several ways. One way that we indicate here is that, I mean, is a direct sum that I mentioned. Take 2 3 1 3 and sum them up. Okay? The repetition code we have in the pocket all the time. Use the direct sum and get the lower bound. And check the entry above. Recall that 6 2 5 would have been MDS, so it is out of league. There is no such code. So the next candidate again 6 2 4. Once it is checked, up to the equivalence we get a unique code, which happens to be what? GG transpose is 0. What does that mean? Sorry? GG transpose invertible means LCD. If GG transpose is 0, then your code is contained in the dual. It is self-orthogonal. Okay? So this one is self-orthogonal, hence not a LCD, and 3 is what you can get. So for 7, we have 4. Again, the highest possible is 6. Okay, out of league. So, for 5, here, there is an LCD code. Again, you can check over magma. And this is LCD. And actually, I mean, given the Grassel's table, this is the best you can do. Because on Grassel's table, I mean, he considers all the bounds that is existing. I mean, not only singleton bound that gives rise to being NDS, of course, but all the bounds. By the way, I am just passing, I mean, the definitions of MDS or anything by assuming that you saw them in the first week. Please interrupt me, I mean, if you get stuck in anything by asking, hey, what is MDS? I don't know. I mean, it's okay. I can tell you what it is. I just assume, I mean, many technical stuff. I hope you are still following. Okay. So, you can make a symmetrical definition, of course. I mean, you can fix the length and the minimum distance, and you can check the best possible dimension that you can obtain from this. Okay? I mean, symmetric definition that you can make. And of course, you have the analogs of the previous results. Okay? I mean, like full space code. Okay? That gives you this. And of course, the repetition and the parity check code now gives you this. I mean, it is an analog result in terms of now fixed length of minimum distance. Proofs are very analogous, and there are more constructions actually concerning more technical stuff. I wanted to skip them because for this I have to give you the definitions of Plotkin and Griezmann bounds. I mean, using those you can still obtain. I mean, those two bounds are. Oops, sorry. Those two bounds are about are on the size of the linear code that you are working on. So a natural thing to think of is that taking those two bounds, which gives some lower bound on the dimension of the code, and use them to construct LC keys, so to say. Puncturing the extended Golay code gives another one. I mean, there are many constructions that you can find on the paper, but I don't want to explain you the entire paper, because here is the thing. You can fill up the table, I mean, the best you can make by such linear constructions up to some extent. I mean, once you catch something in the short length, you can fill up the neighborhoods by the constructions that I just showed you. But for the general case, you have to do something else about, I mean, what you can do the best. And the most famous method to do that is to use linear programming. Okay? Linear programming will give you a lower bound, okay, either on the distance or on the dimension of the code once you are given with two parameters. I will try to explain you over the fixed length and minimum distance, but I mean, it goes back to the Delsart, I mean, many years ago. So first, you can fill up the table, I mean, for, as I said, I mean, 3-2, 4-2, like 5-2, you can fill it up to any length you wish for the two, and also you can extend it a bit towards the other direction as well by using the products or direct sums, okay? But in order to have a notion about an arbitrary length and minimum distance, the best dimension of the code that you can get, you can use linear programming. It's a nice tool. So, further constructions, by the way, using orthogonal matrices. I guess Lin Sok explained you a bit last week, right? About the constructions using the orthogonal matrices. Orthogonal matrix means, I mean, over the n by n matrices, the group of n by n matrices, you can take an orthogonal one, that means x times x transpose is identity, and you can take submatrices of this by considering a subset of its rows, so to say, to create invertible GG transposes, right? Rectangular cases. So this is one method, and the nice thing about the orthogonal matrices that I want to emphasize you today is that we know how many of them are there. And so we know how many row subsets they have, okay? So we can count them. Counting is important in the sense of enumerating the codes, which gives rise to asymptotic results. I mean, that is a nice thing to use. Another idea is to use self-dual codes. A self-dual code, as I said, I mean, G times G transpose must be strictly 0, okay? Equal to 0. It is a special case of being self-orthogonal. So, self-dual means C is equal to C dual. In that case, if you have a standard generating matrix of that form, let's say identity and X for some X, then this is set as G. G times G transpose equal to 0 means identity plus X times X transpose is equal to 0. And that means XX transpose is invertible. Okay? It is identity in the binary case. Please recall that we are in the binary, otherwise it will be minus identity, okay, still invertible. So, one more example again, using the so-called Golay code and its extension up. Once you extend the Golay code, you can take the redundant part, X is called the redundant part of the generating matrix. You can construct these LCD codes by using that redundant part of the generating matrix. Okay? So, linear programming. We have filled, I mean, all the things that we can do by hand, and the rest will be told by Magma. How? In the classical sense, we need those notions. The weight distribution of a linear code. That means AI is the number of code words that have I non-zero coordinates. That is the weight distribution. Okay? Each AI stands for that number. And we know the code's dimension, I mean the total number of code words is of course their sum. So let's set Pix as the Cryptography polynomial, which is generated by this generating function, where the first one satisfies this, okay? Pi0 is n choose I. So what do we know about the weight distribution? By the definition of the code, we have one zero code word, okay? One code word of weight 0. And up to the d-1, we shouldn't have any code word. By the definition of the minimum distance, okay? Minimum distance means, I mean, it is the minimum weight that you can get. So you have no one of these weights, okay? So, and it is always positive, of course. I mean, you might still skip some weights on the way, but we don't know about that. What we can make sure is those weights are 0. And the next property comes from Delsart. This is actually, I mean, why it is called Delsart's linear programming in some books. I mean, if you are looking for it, for example, in McWilliams-Sloan, you have to look for Delsart before LP. So this is how he connects Cryptography polynomial with the weight distribution, okay? And it satisfies this semi-definite property over the binary codes. And if you separate j equals 0 term by using this, a0 is 1 and pi0 is this, by setting it on the other side of the inequality, you obtain that. We just separated j equals 0 and obtain that because we want vectors of length n, not n plus 1. Okay? After that, all you need to do is to build a linear system of equations, okay, that will be optimized. So to say, this thing, okay? Those, by the way, you cannot find on the paper. I mean, they are not well explained there because, I mean, many people know how the linear programming works, but in case you are not familiar with the linear optimization, I mean, you really have to go check this type of slides. So, this is the first condition that we set here, okay? The first d-1 things are 0, strictly 0, and the rest are positive, okay? And this one is about that Cryptography part, the Delsart inequality, okay? We said minus p, we set the minus here, and the n choose i's are here on the right-hand side, and the left-hand side is characterized by p, where p has entries pij at each sense, okay? The Cryptography polynomials, and this is your linear system, okay? And it is strictly, I mean, this is less than or equal to what you are trying to figure out is the solve it for the weight distribution. Okay? Those x1 up to xn represent the solution for each a1 up to an, and it will be summed up to get the best possible dimension that you get. Namely, you have to maximize this to obtain the best possible dimension that you can get. This is linear programming. Okay? So your solution, the size of the code, 2 to the k, is at least that much. That maximized value. Okay? So how to modify this idea to LCD codes, binary LCD codes? We should always keep those in the pocket. We will just add it. We will just add the condition that will come from being LCD, okay? But, I mean, this is the best you can do, arbitrary binary linear codes. So, as a plus, we want them to be LCD as well. So, we need 2 distributions now, one for the C, one for the do. And what we know from being LCD is that, I mean, if you have a vector of weight I, it is either in part of C or C dual. Okay, that is being LCD. Since both of them span the entire space, I mean their direct sum spans the entire space. So any vector of weight I should lie in between either part of C or part of B. This is the condition. And McWilliams identity for the dual distribution. This is what we know. And by using those two properties, by replacing bi by this McWilliams identity here above, and by doing the arrangements, we obtain this. Okay, 2 to the k 0 is just a parameter that will avoid the quadratic term there. There, actually, there is a beautiful sum j from 0 to n, a n there, but we don't want that quadratic parameter. We want a linear programming, so 2 to the k 0 is for that. And to the Delsart's linear programming, which is this upper part here, we just add this p minus delta plus 2 to the k 0 I n, which comes from here. We can set all these terms in one side here on the right hand side, and then here I will have 0. So those zeros are added here. This term is added here, and here you have the LP for LCD. Okay? Very simple. I mean, using two identities, two observations actually, which is proven, one of them is proven by McWilliams by many years ago, but the only observation is that, okay, if you have a vector of weight I, it should belong to one of them. So then the rest is combined, build the linear relation and calculate. Okay? And the theorem is similar. Actually, this is extended to the LCPs as well, but there you need 4 distributions. Okay? I mean, 1 for C, C dual, D dual. Okay? You have to consider everybody. But it is very similar. I mean, you just work with a huger matrix. Again, you can check the relevant paper that I showed you there. So it is extended in a way that you optimize C, I mean, the dimension of C, and also the D dual, of course, I mean, which will be of the same dimension. And the table that we provide on that LCP case is that we consider, again, D of C equals to the dual distance of D. Because this is what is really interesting in the practice. I mean, you don't want to really minimize those two. You want to do the best you can do to make them equal. I mean, this is the best you can do, so the table is given in terms of that case. D is equal, I mean, DC is equal to D dual D. So, but I didn't want to put that here. That would be, I mean, I don't think if the size of the slide would be enough for that huge matrix, that's why. That's why I'm just saying by words. But this is what you can do for LP or LCD. But here the challenge is, again, I mean, I think you have some computer scientists among you. So here the challenge is to remove that K0 over there. Okay? I mean, currently we have been discussing with some experts in the field to remove that K0 term because it adds one more complexity, so to say. Okay? Here, you are I mean, what we want to actually optimize is that only in terms of M and H. Okay? This is an additional constraint, and that adds a lot on the computational time. You see, it is an exponential thing over here. I mean, and that's why we could only compute up to the length 30, which is very, very small, right? Very small. We couldn't even go up to 50, or even in the binary case. I mean, can you imagine over the arbitrary FQ? No. So here the challenge is those tiny K0s to make it non-quadratic but a linear relation. So anybody, I mean, who volunteers to come up with an idea of how one can get rid of the exponential factors there, you are also welcome. So, any questions so far about anything? Any comments? Well, if not, these are all that I wanted to say for the first slot. Thank you very much.
Thank you, Dr. Buket Ozkaya. This is the end of second session. The third session will be delivered by Dr. Ozkaya at 1:30 p.m. So you can take a break right now. And for Muslim participant, you can go to masjid for Jumat prayer. Thank you.